Good morning. So we were discussing about dust ignition and dust flames. So dust flames are heterogeneous in nature. So if you take a premix burner, you will see that fuel gas plus air can be sent and you get a premix flame. So this is a homogeneous flame. But on the other hand, if you have a burner in which you inject say a dust, a combustible dust like coal dust etc. plus air, and you get a flame. So this is basically an heterogeneous flame because there is a solid dust plus a gaseous oxidizer. So whatever we have discussed in the case of solid fuel combustion, those activities are going to happen here also. That is, first of all, the dust particle, so dust particle has to pyrolyze. So first of all, it should be heated to Tp, and the pyrolysis will occur. So before that, some moisture, if it is present, that will also be released. Then it will leave residues. The residue can be char if it is a charring fuel, that is carbon plus ash, or it may be some impurities in the case of non-charring fuels. And these volatiles, after pyrolysis, the gaseous fuels which are going to come out, that will participate in the gaseous reaction. So the gaseous reaction will occur because of the release of the gaseous fuels. Then for the charring fuel, the char itself will be heated up. Char will be heated up to say temperature char reaches about 900 degrees centigrade, then surface reaction take place. Okay, so this is main thing. So the heterogeneous part is basically the char combustion, which is actually taking place in the surface of the solid. Homogeneous reactions involve gaseous fuel mixing with gaseous oxidizer, that is air. Okay, now commonly the dust flames are seen in coal mines, then industries which handle fine dust, etc., where you will see that the settled dust that does settled on some surfaces will entrain as some gas or some air moves past it, and it will form a cloud, and this will get ignited. So as we discussed earlier, yeah, the solid intact solid may not be flammable, but when it has become dust particles and a cloud has formed, then it will become flammable easily. So the controlling factors also we discussed. I'll just go through that for repetition sake. So you can see that when there is a dust layer deposited over the surfaces of several appliances, as there is a relative velocity, flow of ambient gas or any gases of combustion, etc., the dust lift from the surface, entering into these gases and mix with the ambient gas. So if oxidation is oxidizer, that is air is present, then you will see that it may form a cloud of fine particles which can be flammable. The lift and entrainment of dust particles basically depends upon, so the factors affecting is thickness of the deposit layer. Okay, then viscosity, moisture content, so stickiness, then shear stress, and the material properties. So these are the factors affecting the lift and entrainment. Mixing basically also depends upon the convection in the gas phase, any turbulence, etc. So the cloud which is formed, it has basically some gaseous medium and the dust is entrained into it and it is mixed. So the cloud dynamics depends upon temperature, oxygen concentration and level of turbulence. So once the cloud is formed and the ignition source is available, it may be pilot ignition or auto ignition. So what happens is the deflagration occurs, that is combustion of these dust particles occur, and this is not very simple to understand this. Several modes are there for this. That also we have seen. And when you have some confinement in which this cloud is present, then size and material of the confinement also will affect the dust combustion. So overall, the dust deflagration, that is subsonic propagation, subsonic propagation of flame in dust cloud, in the dust cloud. So here we have seen several things. First of all, the particle size, density, chemical composition, pyrolysis temperature for the dust cloud. They are affecting factors. Then in the burn gas, where there is a flame zone, basically the chemical reaction rate, gasification time, flame thickness, etc. are the controlling factors. Then within the dust layer, the dust layer thickness, material property, shear stress, moisture, and relative velocity of the gas, etc. will cause dust lifting and entrainment. They will affect this. Basically, finally, within the confinement parameters like construction type, materials, etc. will be affecting this, the deflagration. That is, when there is a dust layer deposited over a confinement and there is a movement of some gases which also have some additional oxygen, hot gases, then the dust lift and enter into this and also burn along with this mixture. So that dynamics or deflagration is affected by these factors. Now, dust flames, as I told you, there are several modes in dust flames. Previously, researchers, say Sun et al., they have shown that there are two predominant modes. One mode, or the first mode, is there is an individual diffusion flame around the particles. So, like this is a particle as an individual diffusion flame, and due to the heat transfer from this flame to the adjacent particle, the ignition of the particle occurs, and again this particle will have an individual diffusion flame. Similarly, it will go and ignite other particles. Basically, it is a heat transfer control thing. The dust concentration is not very high, so that the volatiles which are released burn within or around the particle circumference itself. On the other hand, if the concentration is high, the second mode happens, where volatiles are, due to the heat transfer, volatiles are released from several particles. So, a volatile plus air mixture is available for a premixed flame to propagate. The premixed flame propagates and ignites another particle to cause a diffusion flame over this, and again the premixed flame also goes because there is a volatile air mixture present around all the particles here. So, here there is a combination of diffusion and premixed flames. Here it is not so. So, these are the two modes was generally reported by the Sun et al. However, Nusselt and Eckhoff, they have given some updated review on this topic. So, different configurations also were considered in the dust flames, okay, in the spherical vessel or in a tubular burner, etc. So, now main thing is, unlike a premixed flame, the mixture of dust and oxidizer is a multi-phase flow. As you know, that solid phase is also involved. So, where the radiation heat transfer becomes important. So, even in a gaseous flame, if there is soot formation, what happens? The soot radiation becomes important. But if there is a solid particle, the solid particle contributes to radiation. The premixed dust air mixture may not be mixed at the molecular level or microscopic level like the premixed gaseous fuel and air mixture. So, that means two types of flames were reported, Nusselt flame and volatile flame. Nusselt flame, volatile flame, as the name suggests, it is only the gaseous flame, homogeneous flame. And Nusselt flame, on the other hand, is the diffusion flame occurring over a particle, that is heterogeneous flame. Surface of the particles it occurs. Okay. So, basically what happens is once the volatiles are released, volatiles mix with the ambient air, causes a flame in the gas phase. Gas phase heat transfer occurs to the particles. So, dust particles interact with the volatile flame. So, particles are heated, the particles evolve volatiles, again volatiles go to gas phase, mix with air, and this mass transfer and heat transfer become coupled. The volatile gas and vapor burn as a premixed flame. So, Burden and Fletcher reported there are 3 distinct mechanisms for that. So, that means you can see that reportedly lot of people have worked on this, but people have given different suggestions for the mechanisms, modes, and the types of flames, etc. Now, for charring fuel, diversion burning of volatile is followed by the combustion of char. This is accepted by all researchers. For the polymers, melting can occur, then the molten monomer can evaporate and vapor phase burning can occur, or sublimation can occur, can also occur. So, now if we take metal, iron or aluminum, etc., you will see that once these metals are heated, oxides are formed, iron oxide, aluminum oxide, etc., that will form a solid oxide shell, and now it is a porous shell through which the vapor comes out or oxygen goes in and so on. So, this is more complicated. High temperatures are involved in this. 4 zones are observed. Now, finally, the recent research has shown there are 4 zones, namely ambient zone, premixed zone, reaction zone, and convection zone. Typically, seen in a premixed flame. So, now this was reported by Rockwell and Rangwala in 2013. So, based upon 2 equivalence ratios, this analysis has been carried out. This actually yesterday we discussed. We will go through that again for repetition's sake. So, you can see that there is a overall equivalence ratio, that is the total solid fuel which is present, the air which is present based upon the mass of the air and mass of the solid fuel, the overall solid fuel, unpyralized solid fuel, whatever be the equivalence ratio, that is pi u. Now, after heating up, volatiles have come out, the pyrolysis gases have come out or vapor have come out. This has mixed with air, and that will contribute to one of the equivalence ratios called phi g or pi g. Now, based upon the concentration of dust, we have some classifications. Okay, A, B, then C. C is further classified as C1 and C2. So, here A means the overall dust concentration is such that phi u is less than 1. Lean, more air is available, concentration is low. So, in this case, the particles, there are 4 zones, ambient zone, nothing is happening to the particle, no heating, etc. As the particle goes into the flame zone, so this is the reaction zone, flame zone, it is preheated. So, particles are preheated such that all the volatiles are released, and particles also finish combusting in the flame zone itself. Nothing comes out, only hot gases comes out. That is it. A. So, now in this case, only hot gases come out, all the fuel is consumed. More air is there, so additional unburnt oxygen is there in the gases. This is one of the simple configuration where low concentration dust is burning. Now, B, whatever be the Pu, that is phi u may be 1, it may be less than 1, greater than 1, any whatever it may be, but air is supplied at a, or air comes to the zone at a faster rate. That means you will see that in the preheat zone, particles, volatiles are released, and some more particles also, the unburnt particles leave this zone and come to the convection zone or the recombination zone, whatever we call. In this convection zone, you will see that the particles are burning like this, burning particles, that is, it has its own flame and it burns. Here it is possible because the overall volatile based Phe is less than 1, that is, more air is available for it to burn. Temperature also is higher and oxygen also available, so it burns. So this is this region, and finally all the particles are burned out in the convection region. Most of the particles are burnt in the flame region, and the particles escaping the flame region coming to the convection regions are burned because of the high temperature and the availability of oxygen, because Pg is less than 1. This is the second zone, second type of mode, we can say. And third one is C1. In these cases, C case, dense or high concentration particles are there. That means the equivalent ratio is greater than 1. Not enough air is there in this. So in the preheat zone, something is heated, some conversion occurs. But the particle size may be such that what happens is the volatiles are released within the preheat zone and the combustion of volatiles are completed. Also, the particles are converted fully. So nothing, particle does not come out of the this zone, but fuel gases are present which require more oxygen is present here. But in this case, the 5G is greater than 1. That means you see that enough oxygen is not there to burn these fuel gases. So hot fuel gases go away. That is the scenario in the C1. C2, again concentration is higher, Phu is greater than 1. Here what happens is particles release volatiles, but it is not fully converted. Particle size may be higher. See, in this case particle size may be lower so that the particle convert. In this case dust size may be higher, say 150 microns, 300 microns, something like that. Here it may be 25 microns. So based upon the volatile release rate or the particle size after the volatile release, etc., particle can convert at a faster rate if the initial particle size itself is lower. So in this case, the for C2 case, particle size may be higher so that volatiles are released, some combustion happens, but particles escape this, but there is no oxygen there to burn because Pg is greater than 1, not enough oxygen is present. That means the particle will continue to devolatilize in the convection zone. Burning may not be possible unless additional oxygen is supplied. So this is the recent paper which gives the scenario of this. Then we also discuss about the structure in these 4 cases, A, B, C1 and C2. Structure is defined using the temperature profile, the mass fraction of the solid, then the mass fraction of the vaporized fuel or the volatile fuels, etc. So you can see, based upon what we have discussed, you can see that the A, for example, in the A, you will the temperature profile is given that the solids, etc., gases, etc., are consumed within this because there is enough oxygen which is available, so it burns everything. It is burned here. B situation, based upon the equivalent ratio, some particle combustion can also occur in the convection zone, but in the C, particle combustion may not be occurring. Particle conversion happens due to devolatilization in the case of C2, which we have seen. So these are the scenarios which are very complicated scenarios, and again in some configurations we can see other scenarios also. So now let us say if there is a premixed flame with fuel gas and a fuel oxidizer, then what we get is basically a premixed flame using cone angle method or flat flame method, etc. I can measure the burning velocity, laminar burning velocity or laminar burning speed, SL. Okay, now if there is a particle air flame, that is dust particles and air are premixed, and there is a equivalence ratio of 5u. Overall equivalence ratio for solid mass of the air by mass of the solid is such that there is a given 5u. Can we get the burning velocity? Yes, in some cases we can. How to get the burning velocity? So, burning velocity of a premixed particle air flame can be got, but it is affected or controlled by several parameters. Okay, in the case of homogeneous, it is only already mixed. Only chemical kinetics plays a role here. But in this case of a particle air flame, chemical kinetics will play a role little bit later. Before that, the volatile release, gasification rate, volatile release rate, particle size, as I told in the previous case, if particle size is higher, then it may not be having enough time to burn. So, particle size, then the concentration, number of particles in a given volume, that is also important. So, it is not just chemical kinetics. So, for the cases A and B in the previous discussed, we can see that the exponent of vaporization kinetic term and the convection zone temperature are most dominant in determining the burning velocity. Cases A and B, because A and B completely combustion occurs. So, the vaporization or devolatilization, this vaporization in the case of solid particle will be devolatilization. So, this volatilization rate is basically, as I told you, in the solid combustion, it is written as something as an Arrhenius term, and also we can also have a, so that is some order for this, that and the convection zone temperature, because obviously when the particles leave the flame zone and go into the convection zone, the temperature there and oxygen availability, obviously in the case of A and B, 5G is less than 1, that means air is available, but temperature should be high enough for the conversion to occur. So, these two will determine the burning velocity. But if you go for scenarios C1 and C2, the activation energy of the gas phase reaction is the most dominant, because how fast the volatiles are burnt, it is a rich combustion, no. So, how fast the volatiles are burned, already some premixing has happened, how fast the volatile is burning, then the overall kinetic rate, you can say the pre-exponential factor B, E is the activation energy, everything will be important. Similarly, the heat which is released, that also will determine the burning velocity. So, based upon the scenarios, it is not just, see for example, when the homogeneous flame, when the gaseous fuel and gaseous oxygen come out, it is very simple to understand that equivalence ratio is very simple to define, and the SL increases, reaches the maximum around a rich phi and decreases. But here it is not so. Whether it will contribute to rich phi or lean phi, etc., depends upon the pyrolysis rate. Then pyrolysis rate itself will depend upon some pyrolysis kinetics and so on. So, as the fuel vapors are going to come out more and more in a rate controlled manner, we cannot surely say what will be the equivalence ratio at the flame zone. So, the equivalence ratio at the flame zone may change. So, in fact, the 5u is not going to affect much, because 5u is the solid to this, solid to the air, that mass of the solid to the mass of the air, or mass of the air to the mass of the solid particles which are present. But in the case of C1 and C2, this 5u is not going to affect much, because the rate at which phi g is forming later, that is going to affect the binding characteristics. So, out of all this, the particle size is more dominant, slightly more dominant, especially in the fuel lean case, because as we see A and B itself, A, all the particles are consumed in the, converted in the flame zone itself, but in the B, some particles can leave the flame zone and come to the convection zone, because the particle size may be higher. So, in all these cases, the thermal conductivity of the dust is more influential Why? Because sensible heating, the particle has to be heated to release the volatile. Okay, so these are the factors affecting the burning velocity. Now, to understand the burning velocity, especially first we will try to understand when there is a coal dust which is entrained naturally into a premixed flame, how it will affect the characteristics of the premixed flame. So this experimental setup by Zai et al. Is explained here. So you can have a, see, there is a long Bunsen burner tube, there will be, see, the Bunsen burner is there, and you can see at a particular height there will be some holes, 2 holes or 4 holes which are drilled circumferentially in the tube, and here an orifice is placed, and air is the fuel plus air mixture at a given phi is supplied to this orifice, so at high velocity jet comes out. Now covering this portion there is a container in which coal dust is kept. You can replace this coal dust by any other dust also. Coal dust is kept, and coal dust particles, due to this high jet of this fuel air mixture, will get entrained into this tube. Okay, it is contained in a tube like this, and mixes with the, so for example, now out of this holes will get the dust particles entrained based upon the velocity of the fuel air or the mass flow rate of the fuel plus air. So you will get, say for example, if methane is the fuel, or a fuel gas plus air plus dust, some dust will come in based upon the velocity of this injection. So we are trying to create a scenario where dust is naturally entraining a mixture of gas. Okay, now it goes out, and if the dust entrains into this premixed flame, a premixed flame is formed as shown here, but the dust particles will go through this and burn. So how it burns, etc., we will see. So in a simple Bunsen burner setup, instead of allowing air to entrain through the holes in the Bunsen burner which is available, we now consider putting some coal dust which will naturally entrain based upon the momentum of the premixed fuel and air mixture which is supplied here. Okay, so that is the setup. Here the fuel is methane, coal is a coal dust in so Pittsburgh seam coal dust is used here. So you can see that if you see the actual flame, there is a, you can note there is a conical flame which is actually formed by what? The premixed CH4 plus air mixture. Now the particles are preheated as it goes very near to the flame, and it gets ignited and burns. You can see the burning of the particles as they go out. Now this is the actual flame, I mean actual photograph, high definition photograph. Now if you have a shadowgraph setup, I get the gradient of density. Okay, so wherever there is a flame, high temperature zone, the density will be lower, and low temperature, the density will be higher. So you can see that a flame which is formed by the particle is seen like this. You can see that. So when you take the shadowgraph, I will get a conical shape of the flame. Here also you can see dust is going on through this flame, but shadowgraph will not show that dust entrainment, like dust combustion, like the streak of fires which are seen over the premix zone, that will not be seen, so that I can find what is the value of the half cone angle, and from the half cone angle I can calculate, I know what is the mixture velocity u into sine alpha will give you the value of the SL. So this image is processed in MATLAB, and we got the sine off cone angle from which SL can be determined. So, you see this burning of this coal dust across the flame, when it travels across the flame, is dependent on particle size, particle concentration, and phi of the premixed CH4 air flame, mixture. So, these are the factors affecting the SL value when there is a dust which is entering. So, when you do not have dust, you will have a SL, which is, I will say, SL base. If you have dust injected, I will say SL dust 1, dust 2, etc. That is, this dust 1 may be of different particle size, different particle concentration, etc. So that we can compare whether due to injection of the dust, natural entrained dust, whether the SL will increase or decrease. Okay.